Okay, so just to review over the net ionic equations, as you can see for letter B, for your silver nitrate and magnesium bromide being mixed, we wrote our molecular equation first, okay? And if you didn't get it, you can copy it later if you need to, okay, if you want to listen. So just remember for your total molecular, you put things together already the way you learned in pre-AP year. You want to always make sure you balance it, and you want to have your states and matter on there. Then we expanded it out for your total ionic or complete ionic. And so you have everybody in ions. Can anybody tell me why they are in ions? Like, why do we even do this? Does anybody know? Well, because ions have charge, yeah. But what exactly is this whole thing actually telling you? Okay, all right, so we're just throwing in the verbiage, that's okay. So do we understand that in that beaker, you do not have silver nitrate? Like, you do not have this little molecule of silver nitrate like floating around in that beaker, okay? You have silvers floating around and you have nitrates floating around. And since they're not together because they dissolved, right, so they split apart, that's what gives them that ion, that's what gives them that charge. So back to your electrolytes, okay? So that's the whole reason why we even do this. But I do want to point out how we approach this one. So when you're asked to write these out, this is the safe. I know when I did the warm-up, I kind of showed you very quickly how to just write your net ionic, just find the main guys. But this is probably a safer way to do it, is write out your complete ionic, and then you just cross out the ones that actually don't matter. And now what's left over is going to be your net ionic. Okay, so that's all that I'm showing you here. That's why there's little slashes through some of it. Okay, so let's put our focus on letter C. So sodium chloride and lithium sulfate. NaCl, LiSO4, La2SO4. Right? Okay, if these are both aqueous to begin with, what's going to happen? But look at your products. Does anything actually happen? According to what you will see in the lab. The sodium sulfate, is that soluble or insoluble? Soluble, right? So that'll be an aqueous. Lithium chloride, soluble. This one is a no reaction. Okay? So you actually really wouldn't even move anybody, because really what's happening is everybody already split because we dissolve them in water, so now all those ions are just they're just floating around. Nobody is like reattaching. That's what this means, okay? All right, looking at D, sodium hydroxide mixed with phosphoric acid. Okay, so sodium hydroxide, there's our good old hydroxide rules, right? So we have NaOH being mixed with my phosphoric acid. How do you write phosphoric acid, y'all? H3PO4, good. Don't forget that -3 charge crisscross down, okay? All right. Okay, so quick question. What do I have here? In terms of, I want you to think back to your electrolytes. What do I actually have here? What is sodium hydroxide? It's a strong, yeah, but so it's a strong base, good. And what do I have for phosphoric acid? That's a strong acid. Okay, when you have a strong, so we won't get to strong, weak, and all that stuff later. Okay, I'll kind of introduce it to you in the next lab, not this one, but the next one. But when you have a strong, that's what we taught you pre-AP year. So what are your products in a strong? Do you guys remember? Salt and an H2O, right. So the salt It's going to be these guys, and my H2O will be made out of my hydrogen and oxygens, okay? So let's go ahead and make that real quick. We are going to have to balance definitely on this one. You guys give it a go on balancing. Would it help if I put this is going to be a 3. Anybody got it? Oh, what do you got? Shout it out. I was waiting for you. What do you got?
3 NaOH plus H3PO4 yields Na3PO4 plus 3H2.
Good. So we had a 3, 1, 1, 3. Good. All right. So from here, let's go ahead and write out the expanded one, and then we'll cross them out, and then we're going to move on to math. Okay? All right. So the sodium hydroxide, it's going to be split. You guys already told me that. Okay? I'm going to make my states of matter super small. That's what the little squiggly thing is going to be. This is where the subscript just became a coefficient. Did you guys see me do that? Right there? Okay.
For Na, does it go?
Yes, it does. Yeah, I was getting ahead of myself. I'm sorry. Yeah. Your coefficients stay, and your subscripts become coefficients. Yes. Okay. Squigglies. All right, and then we're going to have our Na over here. So sodium phosphate is going to be, I'm sorry, I forgot to ask you guys this. Okay, so our salt. You guys said it makes salt in a water. What is the salt going to be when it's in solution? It's going to be split. It's going to be split into its ions, right? Okay, so we got to put the 3Na plus that PO4, 3 minus again, and then plus H2O you leave together. Okay? All right. What state of matter do we put next to H2O? Liquid. That's where the little fancy L goes. Okay? All right. So looking here, who is your spectator ions? And it really makes it, in my opinion, it makes it super easy. Oh, did I forget the 3 again? Jiminy crickets. Yeah, my bad. All right, but who are the spectator ions? As in, who shows up on both sides? Unchanged. Mm-hmm. Exactly. So, do you guys agree? H plus OH makes H2O? Yeah, that's the main event. That's what's going on. The rest of it is spectators. Okay? So that is one benefit to writing it out the long way, is that then you just look at both sides. Did I cross that on both? Oh, yeah, okay. And you just see who shows up on both sides, and that way they go away. Okay? You guys have any questions for me on that? It's just going to take practice. I think the homework problems, I've been helping them with the homework problems. They're good. So just practice with those and make sure I don't know. Did you guys have to, did we verify if it had to be a 3 minus or if it was a minus 3?
It was 3 minus.
It has to go, so put number with the minus after. Okay. All right. Turn the page to this side. All right. So number 9. So it says calculate the mass of silver sulfide produced when 18 grams of silver nitrate is added to excess sodium sulfide. All right, so this one right here is not really anything special. We're not dealing with molarity, nothing like that, okay? So this one is just going to get us it's just going to be straight up stoichiometry. However, I want you to see this one, and I want you to have this in your notes next to you, because one of your labs, when you do a gravimetric analysis, this is how you get your theoretical yield, okay? So I want you to just put that note next to it. I don't feel like I have to walk you through a stoichiometry thing. I think you guys are perfectly capable of trying that one and checking your answer with me, okay? So we're going to move on to number 10. Of course. By the way, do you guys know what I mean by a gravimetric analysis? So you use that little, you see that filtration going on right there? Right here, this middle station. I have the little funnel there and stuff. Okay, so I filtered out all this copper. Okay, I now can take all that, put it on a scale, and measure how much I've got. That's gravimetric. You're measuring the mass of a precipitate. Okay, and that's the precipitate right there. Okay, so one of your labs, you guys are going to kind of get a precipitate formed, and you're going to filter that out, and you're going to take it, and you're going to measure it, and you're going to check to make sure that matches with the molarity of that acid. That's kind of what's going to happen next. Okay, so I just wanted you to be aware it's regular stoichiometry to get your theoretical yield. Okay? Okay. All right. Number 10 is talking about what mass of iron 3 hydroxide produced when 35 milliliters of a 0.25 molar solution of iron 3 nitrate is mixed. Lots of information here. The best place to start, what do you think? Write out your equation. Figure out what the heck you've got, right? Okay. So we're going to do that. I have a feeling that might be where this ends, so we can talk about the bullet lab. All right, so Fe NO33 plus potassium hydroxide yields, I'm sorry, I'm taking the thinking work out of it for y'all. Okay, and then you would have to do what next? Balance it. There you go. All right. There you go. Yes. It isn't. I don't know why I put that there. Equation. What do we do next? I mean, so it says produce when 35 milliliters of a 0.25 of iron 3 nitrate. So we know that this guy is 0.250 molar, and we have 35 mils of him, right? And then it's mixed with 55 mils of a 0.180 molar potassium hydroxide. What type of problem does this just turn into? Well, obviously, stoichiometry. Limiting reactant. Do you guys agree? We have information about 2 different reactants, and they want to talk about the products, right? They want to know how much is this, like how much of that is produced, right? Do we know who controls it? No, that's a limiting reactant problem. All right, so I'm going to stop here with that, okay? All right, so on your bullet lab, I don't know why I stood up. Oh. All right, so in this bullet lab, you guys have the little, we're going to have these in front of you, okay? Do you guys, what do those look like?
Bullet casings.
They are bullet casings, but what kind of metal?
Copper.
Really?
Brass.
Brass, okay. And we know brass is a what?
Alloy.
It's an alloy, so it's made up of multiple metals. So what your goal is going to be on this is you guys, right, now we're going to find out the copper, all right? So in a nutshell, this is what's going to happen. In a bullet shell. All right. You guys are going to have a copper, I believe it's nitrate. Yes, copper nitrate solution. What color is that solution from past experience? What color is that going to be? Blue, exactly. So you're going to have this bright blue liquid. You are going to take that and dilute it to different molarities and get a bunch of measurements. You need to draw a best fit line, or you will obtain a best fit line from that. Once you have that best fit line, now you're going to dissolve Mr. Bullet casing in some nitric acid, which will turn that liquid now a little bit of blue, and you're going to compare it to that to try to figure out how much of that bullet casing was copper. Okay? So it's kind of a you calibrate a graph that is going to determine, once you get your information, what you have concentration-wise. Okay? So it involves making dilutions. It involves making a graph. Okay? Those are probably the biggest things. So I need you guys to make sure you use your notes and you actually do those. Part of your, no, I put it on the thing. Lab, I think, is Monday?
Okay.
Tuesday.
Monday.
Is it Monday? Okay, what I said. It's Monday or Tuesday, I know that. All right, but please look at your pre-lab and start getting to work on it, because one of the things I want you to do is to graph that and show me a best fit line. You need to take up half a page. That was what the density lab was supposed to prepare you for. So if you're still struggling with best fit lines and knowing how to take a slope and all that stuff, you need to come see me right away, because that's a skill I need you to have for this one. Okay? Cool? Cool. There's 4 pre-lab questions. That's it. If you look at the write-up, I don't need procedures. I need name, date, title, purpose, pre-lab questions, and a data table. If you would like to write the procedures because you want to study it later before AP